single time you search for a contact in your phone, look up a product online, or even fire up a video game, there's a really good chance that there's this incredibly elegant piece of logic working behind the scenes. And it's finding what you need in literally a fraction of a second. So today, we're going to pull back that curtain on one of the most fundamental, most important data structures in all of computer science. To really get our heads around the problem here, let's start with a little thought experiment. I want you to imagine a phone book, a ridiculously massive one with a billion names inside, and your job is to find just one of them. How would you do it? Seriously, how you answer that question is the difference between an app that feels lightning fast and one that makes you want to throw your phone clean across the room. So this isn't just some brain teaser, right? This is a core challenge in computer science. How in the world do you search through these massive, massive collections of data efficiently? Well, the most obvious approach, the one we'd all probably think of first, is to just, start at the beginning. You open to the A's and you check every single name one by one until you find the one you're looking for. This is called a linear search. It's simple, it's straightforward, and for a billion items, it is catastrophically, painfully slow. In the programming world, we actually have a way of grading algorithms like this. It's called big O notation. A linear search gets a grade of ON. That N you see there, it just stands for the number of items. So for ON, the time it takes to find something is directly tied to the number of items. You double the items, you double the search time. With our billion-name phone book, this is not a winning strategy. Think of this chart as like a report card for code. Our ON search, it gets a fair. It's not failing, but it's not great. But look all the way over to the left in that green excellent category. There's something called O log N. That is our goal. That's the secret sauce. That's how you search a billion items almost instantly. So the question is, how do we get there? We get there with a really clever way of organizing our data, and it's called a binary search tree, or you'll hear it called a BST for short. It's just this incredibly elegant solution that takes the simple idea of a binary search and applies it to data that's always changing. The entire structure, the whole thing, is built on one simple, powerful rule. For any item, we call it a node, in the tree, everything to its left is smaller than it, and everything to its right is larger. That's it. That one single property is the key to everything. Okay, let's actually look at this. The tree on the left, that's a perfect valid BST. Pick any node, any one you want, like the root, number 7. Everything to its left, 2, 1, 5, 3, they're all smaller. Everything to its right, in this case just 9, is larger. Now look at the tree on the right. It looks kind of similar, but it breaks the rule. See the node 8? It's to the right of 5, which is fine, but it's also in the left-hand part of the root 7, and 8 is definitely not less than 7, so that's not a valid BST. It broke the one rule it had to follow. So how does this one tiny rule make searching so blazing fast? Well, it all comes down to the power of a strategy you've probably heard of, divide and conquer. Let's actually walk through finding the number 6. We start at the top, the root, which is 7. First question, is 6 smaller or larger than 7? It's smaller. So we know with absolute certainty that it must be on the left side of the tree if it exists at all. And just like that, boom, we've eliminated the entire right side in one step. Okay, so now we're at node 2. Is 6 smaller or larger? It's larger, so we go right. Now we're at 5. 6 is larger than 5, so we go right one more time. And there it is. We found it. Did you see what just happened there? This is the crucial point. Every single time we made a decision, we were able to throw away about half of the data that was left. We're not checking every single item. We are taking these giant leaps through the data, just zeroing in on our target with incredible speed. And this amazing performance, this gets that excellent grade we saw on the report card earlier, O log N. To put that in perspective, for a billion items, a linear search could take up to a billion steps, but a search in a balanced binary search tree, it takes about 30. 30! That's not just an improvement, that is a complete and total game changer. But there's always a but, isn't there? Our hero has a weakness, a kind of Achilles heel. This incredible performance of a binary search tree, well, it isn't always guaranteed. Think about it for a second. We built our example tree by putting numbers in a kind of random order. But what if we don't? What happens if we insert them perfectly in order? Let's say we insert 10, then 20, then 30, and so on. Let's just trace it out. We insert 10. Okay,
That's the root. Then we insert 20. Well, 20 is greater than 10, so it goes to the right. Then we insert 30. 30 is greater than 10, so we check right, and it's also greater than 20, so we go right again. You can already see the pattern forming, can't you? And this is exactly what happens. Our beautiful, bushy, super efficient tree completely degenerates. It turns into this long, spindly stick. Functionally, this isn't even a tree anymore. It's basically just a list, and we've lost all of our amazing O log n superpowers. And this is its key disadvantage. Wikipedia actually puts it perfectly. The performance of a binary search tree is dependent on the order of insertion, since arbitrary insertions may lead to degeneracy. The very thing that makes a BST powerful is also what can bring it to its knees if the data isn't mixed up enough. This table just puts it all in black and white. On average, a BST search is excellent, that beautiful O log n. But in that worst-case scenario we just saw, our spindly little stick, the performance drops all the way down to O of n. That's the same fair rating as a simple list. We're right back where we started. So you might be thinking, okay, if they have this huge potential flaw, why are we even talking about them? Because this simple idea is a fundamental building block for so much of the technology we use every single day. Yeah, the original Doom video game from 1993? It famously used a version of this to figure out what parts of the world to even draw on your screen. The compilers that turn code into programs use them to understand the logic. And maybe most importantly, they are a core concept inside databases for indexing and pulling up records at incredible speeds. Now, it's important to note that computer scientists, being a clever bunch, developed what are called self-balancing trees, things like breadblack trees or AVL trees, that have built-in mechanisms to prevent that worst-case scenario from ever happening. But they are all built on this exact same elegant BST logic we've been talking about.
And that's what's so fascinating to me. A single, simple rule, smaller things go to the left, larger things go to the right, can transform a hopelessly slow process into one that feels almost instantaneous. It really makes you wonder, what other simple, powerful ideas like this are hiding just beneath the surface of our digital world?